So I did warn you way back at the start of Calc 1 that we would be doing limits for the entirety of calculus. So, hey, here they come again. So we've been talking about a sequence, so we're now going to talk about the limit of a sequence. So, right, that sequence is that list of numbers in some sort of order. And so we will talk about the convergence or the limit of a sequence. So here's our definition. For a sequence, and remember we use our curly Q braces, for a sequence A sub n, if the terms of A sub n become arbitrarily close to a real number L as n gets big, we say that A sub n is a convergent sequence and that A sub n equal to L is the limit of the sequence. Okay? So L is that number that those terms, right, in your sequence start to approach. And so if we were going to write this in notation, it looks a whole lot like the notation we use for functions, right, limit of a function. So the limit of those A sub n terms as n goes to infinity equals L. Okay. Now, if A sub n, right, if that sequence is not convergent, then, right, its opposite is going to be divergent. So it diverges. We say the sequence diverges if it does not approach a specific number. Okay, if the terms do not approach a particular number. Now, again, just like for limits of functions, we had limit laws. These are going to look super familiar. So the limit laws for sequences. So let's let the limit of A sub n as n gets big be capital A, and the limit of a different sequence, B sub n as n gets big, equal capital B. It's completely intuitive. Don't fight it. So the limit of, right, the sum or the difference of the two sequences is, right, the sum or difference, right, of the limits. So capital A plus or minus B. This is where, right, you can, limits are different than, right, some other things, and it works for products and quotients. So the limit of a product of two sequences is the product of the limits. So capital A times capital B. The limit of a quotient, I guess I should be writing as n gets big, as n gets big, as n gets big. N goes to infinity, or n gets big, right? So capital A over capital B. And then C, this is just our constant multiple coefficient. Let me just slap a coefficient on there. And I know you know what this is going to be, right? C times A, right? C times the limit of that sequence A sub n. So what we're going to do then, right? So this is finding out if it converges, what does it converge to, or does it diverge? How are we going to check it out? Right? So there are a couple of different strategies. I'm going to use my calculator. I'm going to be writing some terms. I'm going to be pulling in some algebra types of things. Right? So let's just take a quick little look here. So let's look at this first sequence that I have. So I have A sub n, my general term is 8 minus 3 over n squared. So we're trying to think of what happens to these terms as we start writing them out as n gets really big, right? So maybe I'll write a couple, but I'm not going to write a lot because then I'm going to be doing fraction math and nobody wants to do that, right? So, right, if n equals 1, our first term is 8 minus 3, so our first term would be 5. And our next term as, let's see, n is 2, so now I have 8 minus 3/4, so that'll be 7 1/4. And then when n is 3, I'll have 8 minus 1/3, so that'll be 7.67. Okay, I'm getting totally lazy. N equals 4. Okay, I'm already lazy. Do you guys all see what's happening? So this term right here, this 3 over n squared, as n gets big, that last term is going to start, right, taking less and less away from the 8. So this term is going to go to 0. So we would say that this sequence, right, this sequence of A sub n converges, and its limit is 8. If I kept writing out those terms, they would head towards 8. Okay, let's take a look at number 2. So this sequence is 1/2 to the n. So let's write out some terms. Let's see what it looks like they're headed towards. So n equals 1, 1/2. N equals 2, right? So this is n equals 1. N equals 2. So I have 1/2 squared, so that's 1/4. N equals 3. 1/2 to the third, so 1/8. N equals 4. 1/16. Dot, dot, dot. What's happening to these terms, right? They're getting smaller and smaller and smaller and smaller. Is there some number that it's going to kind of like hold them up, that they're not going to go below? Exactly. So we could say that this one also converges, the sequence converges, right, to L equals 0. Or you could say it just converges to 0. Right, so these individual terms keep getting smaller and smaller and smaller. Now, right, the limit is 0. We will never actually get a term that is equal to 0, but we can get, right, as close, as arbitrarily close as we want by taking a large enough n. Okay, what about number 3? How would we figure out what the limit of this is? And it really is just like how we did limits of a function. So if you want to pull in some L'Hopital, if you want to pull in some, divide everybody by n squared and see what happens as n gets big. But right now, right, what we've been doing is taking the limit as n goes to infinity of, right, this generic version, right, this generic term in our sequence. So, right, as n gets very, so let's go ahead and divide each of our terms by n squared. That's our highest power of n. And then we'll get, right, 6 over n squared plus 1 over, right, so the n squareds would cancel here, so I'll get 3 plus 2 over n minus 1 over n squared. And now we're taking the limit as n goes to infinity. And as n goes to infinity, all of these numbers that have n's in the denominator are going to go to 0. Being told my audio is really quiet here. Sorry about that. Let me try to bump it up. So I can go ahead and just zero out anything that has an n in the denominator, because as n gets big, that term right, goes to 0. So we're going to have this limit then goes to, what do I have left? I have 1/3, which is also, right, 1 over 3. So this is also convergent. If it has a limit, it converges. Okay, next one. N gets big. So we're taking the limit as n gets big of e to the 5 over n over 2n plus 1. Right? I like to put this one on tests because, right, you can't, this is not an easy calculator answer. So really we're looking at what's happening to this exponent as n gets big, right? So this is kind of like the one we just did, but now I'm going to talk about, right, a different strategy for it. So this is the one where you would do, right, if the degrees are the same, you can just do the leading coefficients. Do you guys remember that from your pre-calculus lives? So this is going to behave for really big n. This is going to behave as e to the 5 halves, right? This plus 1 isn't going to be contributing a whole lot at all. So that is going to be, right, the limit of that sequence. Okay, 5. 1.2 to the n. So this one I'm not really sure what I would do about it. Maybe I'd write out a few terms. So if n equals 1, I've got 1.2. I'm going to grab my calculator. If n is 2, so I have 1.2 squared, that's 1.44. And 1.2 cubed is 1.728. and 1.2 to the fourth. Okay, I don't see anything. I don't see a pattern showing up. 2.0736. I'll do one more. 1.2 to the fifth. 2.48832. You know, they just keep getting bigger, and I don't see a large number that's going to kind of like bound them from above. So I think this is going to be I know this is a divergent sequence. And I don't know if you guys noticed this or recognized it from, right, what kind of a sequence this is, but this would be a geometric sequence. There's that common ratio of 1.2 between each of the terms, right? And so as a rule, a geometric sequence will diverge if that ratio is bigger than 1. So in this case, our ratio is 1.2, right? So this one would diverge. Okay, so number 6. Again, we're just going to write out some terms. So the first one, so if n equals 1, I have -1 to the 1, that's -1. If n is 2, I have -1 squared, that's +1. If n is 3, -1 cubed, that's -1. -1 to the fourth, +1. Do you see what's happening? It's just oscillating back and forth between positive and -1. So this one is not approaching any one particular number. It's just bouncing back and forth, right, between plus and -1. So this does not approach a particular number. So this one we would say is also a divergent sequence. Okay, so it's approaching, right, two separate numbers. It never varies from those, but it doesn't approach one particular number. So the limit has to be exactly one number that your terms are approaching. Okay, just a little bit more. So a squeeze theorem. So this is what it is. So we're going to use squeeze theorem. So it came up back in your trigonometry class, right? We're going to see it again this term. So just trying to get your brains thinking in that way. So let's let A sub n, B sub n, and C sub n be 3 separate sequences such that for some number m, okay, so this is another one of those desensitizations. Sorry, my dog's having a conversation too. So for some number m, don't worry about it, A sub n, right, all of the terms of your A sequence are sandwiched between B sub n and C sub n. Okay, so you're writing out your terms, and at some point you get to a place where all of those A terms of your sequence that you would write out lie between the terms of B and C. Okay? Now this upside down capital A, in case you didn't remember, this is our symbol for all, right? For all n's that are greater than m. So once you pass this point, right, where right, your A's, all of your A's live in between B and C. Okay, once you pass that point, if A is always in between, then if the limit of B sub n as n gets big equals the limit of C sub n as n gets big, and those both equal some number L, right? So if A is sandwiched between and the limits on either side approach L, then we can say that the limit of A sub n as n gets big is also L. And I have no idea what my dog is doing. Okay, so finding the limit of a sequence.